Hi, this is a second in a series of temperature and heat. This one's on heat. So remember with the temperature video we said the temperature is just a measurement of the average kinetic energy of the molecules in the substance. So what is heat? So heat is a form of energy. It can be transferred. That's the important thing about heat. You can transfer heat from a hot object to a cold object, and they'll reach equilibrium when the two objects have the same temperature. We call that thermal equilibrium. And as with all units of energy, including heat energy, the units for heat are the joule, named after James Prescott Joule. So as most you've learned in your 8th grade physical science course, energy will do work. And so a joule is the amount of energy that'll do a certain amount of work. Actually what it will do, it'll lift a mass of 0.102 kilograms, that's like a small apple, 1 meter high against the Earth's gravity. So I've got an apparatus set here that'll show us better what a joule is. And the star of my apparatus is my candle. I've predetermined it to have exactly 1 joule of heat energy stored in it. I'm going to put the candle inside this cylinder, make sure there's 100% oxygen in this cylinder, open the little valve, put this piston, which is an airtight piston, down into the cylinder. Now remember the valve's open at the bottom, so the air gets pushed out, and that's probably good enough. Then we're going to mark the bottom of the top of the piston actually, and we're going to set our apple right there. We want to know how far we move the apple in the end. So let's get our apple and place it on the piston. Might compress it a little tiny bit, so you might see that fall, but I'm not showing that here. And now let's light the candle. And when we light the candle, what's going to happen is the air is going to expand inside, and it's going to lift the piston up. And as the candle burns out, because remember it's only got 1 joule of energy in it, the piston's going to stop. And so we're going to have no more candle left, right? So let me just put the candle's gone now. And let's mark where the apple got lifted to. So if we mark the position of the apple where it finally went, and if we get a ruler or a meter stick and what we're going to measure, since that was 1 joule's worth of energy, what we're going to measure is this length from here to here. This length is exactly 1 meter. And since we had the apple, which was 1 newton of weight, right? So 1 newton of weight, and we move the apple 1 meter. So we've done 1 newton meters worth of work, which is equal to 1 joule. So we've done 1 joule's worth of work, and remember we did that all from the 1 joule of energy that was produced by the burning candle. So hopefully you understand better what a joule is now. So heat can also be measured in units called calories. Calorie is convenient when you're trying to actually measure the temperature change in water. The amount of heat required to raise the temperature of 1 gram of water by 1 degree Celsius is a calorie. And if we look at what a gram of water is real quickly, it's a little cube of water that's 1 centimeter high, 1 centimeter wide, and 1 centimeter thick, known as a cubic centimeter. So if you had a little cube, all these dimensions, the back dimension, how thick it is and how tall it is and how wide it is, are all the same dimension, 1 centimeter, then that's 1 centimeter cube, 1 cubic centimeter. And now if we fill that with water, it's not going to hold very much. It's about 22 drops of water. That's going to equal in volume to 1 milliliter. And if you were to weigh just the water inside, you would get 1 gram. And it's an important distinction maybe to note that that's at the most dense point. The water exists at 4 degrees Celsius. All right. So if we had a gram of water, which is a cubic centimeter of water, we fill this up. And let's take a little birthday candle. And let's burn the candle for however long it takes to heat that water, let's say from 20 degrees Celsius to 21 degrees Celsius. So our change in temperature, delta T, stands for change. It's the final minus the starting. So final is 21 minus the starting is 20, and that is 1 degree Celsius. So that took 1 calorie of heat to change that temperature of the water in the cube by 1 degree. That's what a calorie is. Okay, so calories actually come in 2 sizes. The calorie I just described to you, known as the small calorie, it has the unit little cal for calorie. And a large calorie, there's no kidding here, has a unit big cal for it's got a big C in it for kilocalorie. A large calorie, known as a kilocalorie, is the kind of calories that food is measured in. So what's the difference between a large calorie and a small calorie? Simply the amount of water that we're heating. In a large calorie, we're heating 1 kilogram of water, which is a liter. And in a small calorie, we're heating 1 gram of water, which is a milliliter. And so if we want to calculate, how many degrees Celsius does the temperature rise from a 2-calorie breath mint, well, we'd have to make sure we're heating the right amount of water. So we're going to heat, in that case, we're going to heat 1 kilogram of water, right? So you get a bucket exactly at the kilogram, or 1 liter, right? 1 liter of water in it. And you put that bucket in a sealed container. And you have oxygen in here. You got your little breath mint down in the bottom. Lots of oxygen. And now you can heat this breath mint by lighting it on fire in the oxygen. And of course it's going to heat the water. And that 1 kilogram of water will heat up 2 degrees Celsius if it's a 2-calorie breath mint. And so we'll get 2 kilocalories, or just we say 2 big cal. So that's how they get a 2-calorie breath mint and test it for its caloric value. Now I oversimplified this bomb calorimeter, but basically what they do is they just burn the breath mint, or burn the food that they're testing, and heat a kilogram of water and see how many degrees Celsius rise that is. However many degrees Celsius, take that times the mass of water. Usually for simplicity, we just use a kilogram of water, right? You don't have to use a kilogram of water, because what if we used 0.5 kilograms of water? What would happen is the water would rise 4 degrees Celsius. That would still be 2 kilocalories. So that's how you can measure heat in the form of calories, both the small calorie and the large calorie. Okay, so the large calorie and the small calorie have to be able to be converted into joules correctly. So we've got 1 small calorie equals 4.18 joules. And 1 large calorie, a kilocalorie, right, that's the kind that food's measured in, is equal to 4180 joules. Or we could simply say this: 1 kcal equals 4.18 kilojoules. So those are the important conversion factors when you want to convert calories into joules, or kilocalories into joules, or kilocalories into kilojoules. Okay, let's look at one of the other important aspects of heat, and that's the fact that it can be transferred. Basically, 3 ways that heat can be transferred: radiation, conduction, and convection. And let's first look at radiation. So radiation via electromagnetic rays in the infrared spectrum. Electromagnetic rays are rays just like light, except the heat wave that we're looking at, we can't see it with our eye. But there is a neat experiment you can do. Let me show you that experiment real quickly. Just take a remote control and point it at a camera and push the buttons, and you'll see the little infrared light being given off. So that just shows you that even though we can't see electromagnetic radiation in the heat infrared range, digital cameras and things like that can. So heat travels through electromagnetic waves just like light does, except it's a longer wavelength than light. It's under the red. Red's the longest wavelength that we can see, and under red is infrared. That we can't see, but it travels just like light, 300 million meters per second, and that's one way heat can be transferred. And a second way heat can be transferred from one object to another is by conduction. That's where the molecules are jiggling and jostling one another, and from the hotter end of the material, they start jostling really hard, and then they transfer their kinetic energy to the molecules next to them by bumping into those molecules. That in turn speeds those molecules up, and they jostle faster. And this just creates a path of energy transfer from the hot area to the cold area until the entire substance has reached thermal equilibrium. So conduction is where the molecules push each other next to each other and just keeps traveling down the substance. And a third way that heat can travel from a hot area to a cold area is by convection. Convection is a method in which currents are created in a fluid. Fluid can either be gas, air, or it can be actual liquid, like magma in the earth. And these currents created in the liquids cause the low-density, hotter fluid or liquid or gas to float upward, and the heavier, cooler, more dense fluid on top to flow downward. So you just get this pattern. Let's draw a beaker of water being heated on a burner. So if we had a burner underneath here, we can just have this water, and the hot molecules here will start rising because they're less dense than the colder ones on top. And once they get to the top, they cool off, and so then they start going back down, and they heat up when they're down here, and then they go up. So you get these currents of cold, sinking molecules and hot, rising molecules as to their density, and that's convection. Same thing happens in the Earth. Deep in the Earth, we've got this magma deep in the Earth, and the deeper you go, the hotter it gets. And then on top of the very outer crust, remembers the plate. So I'll just try to draw a plate here with all the landforms that you'd see on it, mountains and lakes, and well, lake isn't landform, but you get the idea. So you got mountains, valleys, streams in the valleys, and this plate is very thick, rock. But under that is this magma, and you have the hot magma rising up and pushing on the plate, and then the plate's going to push that way because the magma comes up and flows and pushes on it. And then when the magma hits the plate, it's cooler. It gets heavy, of course, and sinks, or it gets more dense, I should say. And then down in the center of the Earth, the hotter magma rises again, comes up, pushes on the plate. And the plate normally doesn't move, but when you get this magma pushing hard enough, the plate can move, and that's a cause for an earthquake. So they didn't understand what drove plate tectonics, and they found out that it's the convection currents in the magma that's the engine to move the plates around the globe. So now you have a connection between your chemistry and physics and earth science.